Welcome to the satellite communication course. Now we learn here the cloud attenuation. That cloud attenuation in the tropospheric region. Cloud attenuation occur at the tropospheric region. Now that cloud is consist of what? A cloud is consist of a liquid water. Liquid water droplets. And that liquid water droplets, they have the diameter. That diameter it will be less than a zero point 0.1 mm. Okay, that cloud droplet. And they have the water content, and that water content is from the 0.05 to 2 gram per meter cube. But if you consider that a cloud attenuation, but a cloud attenuation that will be less than the rain attenuation. We can say that a cloud attenuation is lower than the rain attenuation. But but if you consider that because of that liquid water droplets we have, and they have the water content there, so even if that rain is going on there, or at the presence of a rain, whatever the cloud or that particular water droplets we have at that particular period of a time, so then attenuation occur because of that particular cloud droplet. And again we can say that a cloud attenuation, again it is a function of frequency there. I can say that it is, or it is depending upon the frequency, function of frequency and a elevation. So that's why that elevation angle is important. I'll just write elevation angle here. Whenever we consider that a earth station, so that elevation angle is important. So generally we say that a cloud attenuation is a function of a frequency. So that's why if supposed to be frequency or that elevation angle increases, that cloud attenuation increases. You can say that a cloud attenuation that will be increases when we have that frequency, and that elevation angle that will be increases there. That's why the total attenuation because of the cloud, that will be given by At is equal to L, then we have a Kc here, then a sine of a theta here, and that will be in a dB. Now in this case, that L is nothing but what? A total columnar content of water, and that will be in kg per meter square. So attenuation that is depending upon L into Kc by sine theta, and that L is nothing but a content of a water, and then we can say that a Kc is nothing but a specific attenuation coefficient, specific attenuation coefficient that will be depending upon the dB per kilometer, that is the water length by meter cube. And that theta we say it is nothing but a elevation angle in the range of 10 degree to 90 degree. And that specific attenuation, if we calculate that, because that kg is a specific attenuation coefficient, so that a specific attenuation gamma c is equal to kc into m. That, that gamma c is nothing but a specific attenuation that within a dB per kilometer value here. We have that kc, and that kc is a columnar content, that kc is specific attenuation coefficient, and that specific attenuation gamma c is equal to kc into m, and a m is nothing but that liquid water density, and that liquid water density in gram meter cube. But these values of the specific attenuation coefficient, that kc here, and that kc is a different at a different frequency. Again, that kc is a different at a different temperature. So, means specific attenuation constant is different at a different frequency as well as a different temperature there. So now we should know that what will be the specific attenuation constant at that particular frequency or a particular temperature there. And again we say here a total cloud attenuation that will be depending upon here this L, that is about the water content. It is depending upon the frequency here, and this one is about the elevation. So means we have a water content, and then we have this frequency dependent, and this one we are saying that about it is depending upon that elevation angle. So as we say that a cloud attenuation, it is a function of frequency and elevation. Cloud attenuation is a function of frequency and elevation, and cloud attenuation increases if that frequency and elevation angle changes. Here, so if that frequency changes, your cloud attenuation changes. Increases cloud attenuation and increases if that frequency and elevation angle is increases there. Means we can say that increasing the frequency at cloud attenuation increases if we have the frequency increases and theta decreases. Okay, we can say that frequency increases and a elevation angle it will be decreases there. So that's why that is about a total attenuation is a function of frequency for the different elevation angle. Okay, cloud attenuation is a function of a frequency for the different elevation angle, and again it is depending upon that what will be the clouds and what will be the cloud depth. What will be the we have the cloud depth, and what will be the water content or liquid water content in that particular cloud there. Okay, liquid water droplet or liquid water content in that particular cloud there. So now if you see the graph, that is about a specific attenuation constant. Okay, so if you see a graph here, here we have the specific attenuation coefficient, that is about a kc here, and we can consider that this one is about a frequency here, and that frequency is from the 5, 10, 20, then 200 now. And this one is about a specific attenuation coefficient. Specific attenuation coefficient. So from 0.01, 0.02, 0.05, then 0.1, 0.2, zero point 0.3, then 1, then 3, 5, then 10 here. Okay, so like so if you draw a graph here. So in that case, you can see that there will be attenuation. Okay, there will be attenuation from this. Likewise, we have the attenuation here that will be up to 10 here. Okay, so this one. Okay, and then attenuation. Likewise, we have then we have the attenuation at this. Likewise here, all these are made at that particular 100 gigahertz or a 200 gigahertz of frequency there. But that will depending upon that how much will be the temperature at that particular place here. This one is about 8 degree here. So this one is about 0 degree Celsius. This one say it's about a 10 degree Celsius, and this red one is about a 20 degree Celsius. And this one is about a frequency. It is in terms of a gigahertz. So attenuation constant, okay, that will be changes that attenuation coefficient and this frequency. Means if you say now here, so frequency increases, so specific attenuation constant that will be increases, and because of that, 80 is depending upon that specific attenuation constant. So now we say that here it is depending upon that a frequency. So now if you consider that a satellite operating at the different band of a frequency, L band, C band, and so higher the band, so means what we can say the frequency is a larger, so attenuation will be larger. Means a cloud attenuation will be larger at the highest frequency. Next we consider here the rain attenuation. Consider the next topic, that will be the rain attenuation. Now in the case of a rain attenuation, then again that rain attenuation that is again occur or that effect will be occur when we have the troposphere or a tropospheric. So attenuation means your signal get attenuated in that tropospheric region or at a troposphere when the frequency of a signal that will be frequency above the 10 gigahertz. Rain attenuations occur when we have the frequencies that will be higher than the 10 gigahertz. Then and then above the 10 gigahertz of a signal frequency, that attenuation due to the rain, your signal get attenuated due to the rain here. And again that rain attenuation that will be depending upon that rain as well as type of rain. Okay, so you can say that's about a rain. Then again it is depending upon that wavelength because it's nothing but frequency there. Then again it is upon a rain rate here. Then what will be the drop size of the rain here? That drop size. So that's why it is about a distribution we say, or you can say that about a drop shape. So generally, if you consider that there are the various structures of a rain, we can say that a rain structure, and that will be rain structure is about a stratified rain. Then we have the rain, convective rain, and we have the rain that will be a cyclonic rain or a cyclonic storm. So just like we have, it's nothing but a type of a rain we consider here. So generally, if you consider that a stratified rain, that is nothing but a it is a typical horizontal extension of that particular whatever the rain, and they have the that particular attenuations occur, that is rain rate under that at 25 millimeter per hour. Generally, it can be a, if you consider that, it can be a horizontal or a uh, vertical in nature, and that will be that drops, okay, rain drops, we can say that, and that attenuations occur above the at that particular troposphere. So we can say that attenuation occurs at the 4 to 6 kilometer above the 4 to 6 kilometer from the Earth station. Okay, and that it that again we can say that above this particular it will occur with that particular rain rate. Generally, we can consider that, but it is not a fixed here. It will be vary. Okay, rate at this particular rate we supposed to be considered. There may be a small variation in that particular rate, but above that particular uh, height or a altitude, that attenuations occur. If you consider that a convective rain, so that rain that moves vertically, okay, this convective rain moves vertically and that extends horizontally over hundreds of a kilometer. Okay, it moves vertically and extends horizontally over the hundreds of a kilometer there. So we can say that above that 100 kilometer of a height. And that convective rain is about above that particular height, or you can say that that height is nothing but a freezing point or a freezing layer there. Okay, that will be of a freezing layer. We have say that about a convective layer. Then a cyclonic storm or a cyclonic rain, we say, and that will be nothing but in the fashion in a circular fashion. It will be in a circular fashion, and they have the diameter of a 50 to 200 kilometer of a diameter, and they move with a speed of what, 10 to 20 kilometer per hour. They move with a speed of a 10 to 20 kilometer per hour, and their height that will be extended to the melting layer, and that will be up to 8 kilometers. And they have the high rain rate of 25 mm per hour. Okay, they have the high rain rate that will be above this 25 per hour. Yeah, that is about it. So because means we can say that there will be some motion, there may be a horizontal or a vertical, there may be a cyclonic circular motion of that particular rain, and due to that particular motion of the rain front, there will be high rain rate duration, and that duration will be short, and because of that there will be more attenuation. So that that attenuation of your signal that will be propagating through this particular rain, and that will be depending upon that what will be the distance, means rain through distance, or we can say that what will be the particular path. So you can calculate that attenuation A is equal to what, with the rain through a distance L along that particular path, we can consider that A is equal to what, alpha into delta x. So L is nothing but the distance here, and alpha is nothing but a specific attenuation. Alpha is a specific attenuation here. That specific attenuation of a rain or that particular volume, that will be expressed in terms of a dB per kilometer. And that alpha is approximately is equal to A into R raised to B. Alpha is equal to what? A into R raised to B. That R is nothing but what? A rain rate. And that rain rate can be expressed in terms of a millimeter per hour. And that A and B, that A and B, these are the constant, and that will be depending upon that temperature and a frequency. Okay, these are all these A and B, these are the constant, and that are depending upon that temperature and a frequency. So that total attenuation, if you consider that total attenuation is depending upon that the wave is propagating through that particular path, or wave is propagating through that particular range distance. Okay, whatever the range distance is. Or this means we generally we say that we consider supposed to be this about a attenuation here. The wave is propagating through that particular. So how much will be the distance of that particular range? Okay, that is about, or what will be the path of that particular signal propagating through that particular range there. So that's why that distance is in terms of a kilometer there. So that's why we can calculate that a attenuation or attenuation of your wave propagating through that that rain here, that will be depending upon that A, that R raised to B here into that L, that will be a dB. That is about the rain attenuation. This is nothing but the rain attenuation. But the factor of A and B, okay, this A and B, that will be depending upon that frequency. A is equal to what? That will be what? 4.21 into 10 to the power minus 5 F raised to 2.42. But when this A value at 4.21, when we have the frequency is in the range of 2.9 to the 54 gigahertz. Again, the A value can be changed. It will be 4.09 into 10 to the power minus 2 F raised to 0.699. When we have 54 F less than or equal to 180 gigahertz. Then value of that B is equal to what? 1.41 F raised to minus 0.0779 when we have the frequency is about 8.5 to F the 25 gigahertz. And B, we can say that 2.63 F raised to minus 2.72. And we have the frequency from the 25 gigahertz to that is equal to or greater than 164 gigahertz. Now that is about the values. All these values of a V here, that A and B, all these values are depending upon that frequency. So what will be the range of that frequency which you are transmitting when we say that uplink signal frequency or downlink frequency signal frequency. So in that case, A and B will be changes so that we can calculate that attenuation directly with respect to the particular frequency there. Generally, we can consider here that a rain attenuation, we say that what will be the attenuations of a rain occur. So in the particular case, we say that we have the earth station. This is about our earth station now. That earth station has some particular elevation angle and it is transmitting the signal to the satellite. Satellite is somewhere in this particular space here. So at that particular height, at this particular specific height we say here, And this is about the signal transmitting through this. That is a signal transmitted. That is to the satellite now. Signal is transmitting toward the satellite. But this point is called as a frozen point. This point is called as a frozen point. That frozen precipitation, and you can say that liquid. And that about the length, or you can say that about a path. We say your signal is transmitting. That path is from the earth station to this particular frozen point. Okay, that is about the, can say that's about the length we have. And this one is about the a earth station situated, we say that, and that earth is having some particular height at this particular height. But if you consider that this one is about a horizon, we say from the sea, this, or we can say a sea level. So in that case, this will be the height, and that effective height from the sea level to your earth station. That is about the height of this earth station from the sea level to the ground. Okay, surface. This one is about a height. So we can consider here. We can say that we have the rain occurs. Likewise, that is about a rain this particular region. This one is nothing but the rain we say, and this is about the angle theta. That is nothing but the elevation. So we can calculate that the effective length, that L, is equal to what? HR. So this is about H0 we can calculate here. We can calculate here with respect to the values now. Okay, sine of theta kilometer. That is about the effective length. So what is the effective length? That is about the attenuation. A is equal to what? A into R into L. L is nothing but the effective length, and that effective length is to be obtained using the earth station altitude here. This is about earth station altitude now from the sea level here. And this one is about, we have the height height of that particular rain column. This is about a rain column. Here this one is about a freezing point from ground station to the that particular freezing point. That is about the height we can calculate. And this theta is nothing but the elevation angle. So this HR, this one is, you can say that is about a height of the rain column. Okay, and this one is about a altitude. This one is about a altitude, and this one is about a elevation. Theta is nothing but the elevation angle. So that L, effective length L, is equal to HR minus H0 by sin theta in terms of a kilometer there. So this will gives us the effective length, and from that effective length you can calculate that what will be the attenuation. Next factor is about a scintillation. Now the scintillation is nothing but what? a rapid change in the attenuation of your wave or a signal. Scintillation means what? A rapid changes the attenuation of the signal there. Why this rapid changes occur? Because a rapid fluctuation in the signal received occur. That's why that scintillation we say that scintillation we observe because of that a rapid changes in the attenuation. Okay. Now we can say that a scintillation observed as a rapid fluctuation in the received signal or rapid changes in the attenuation of that particular received signal, and that is nothing but the scintillation we say. And the scintillation occurs because of a scattering irregularities in the ionospheric layer, and because of that irregularities, which means scattering means what? Because of that particular layer, when your signal is propagating through that ionospheric layer, signal gets scattered. So because of that signal scattered, so signal get that position of that signal changes, means drifting their original changes in the position or drifting occur. So means but that particular scintillation occurs when your signal is propagating through the ionospheric layer at that particular frequency. But ionospheric layer occur in a daytime because of that particular solar radiations and all. So free electrons and ions there. So because of that, your attenuation of the signal occurs. But what happened here? Means in a daytime, due to that ionization effect, your signal get attenuated. But when we can say that in the night time, okay, because we say that ionospheric layer is present in the day. This is about because of that. This is about the ionospheric effect. So because of that, signal attenuated. But in the case of a night, when we have that solar radiation disappears, so in that particular case, so there may be variation in the ionospheric layer. There may be a variation in that particular ionospheric layer. So because of that variation in that ionospheric layer, so that a scintillation occurs. So that scintillation occurs because at a particular troposphere with a low elevation angle. Scintillation occurs due to the variation in the troposphere, variation in the troposphere here. Okay, or we can say that because of that low elevation angle, that a scintillation occurs. And that scintillation means what? It changes the amplitude and phase of the signal. Means we can say that a amplitude and a phase of a received signal. Okay, that amplitude and phase of a received signal changes. And why this occur? Because of that variation in the that timing or variation in the ionospheric layer. And that variation causes because of the day or a night. And because of that variation in that ionospheric layer, that scintillation occurs. Next, about a depolarization. So generally we say that a polarization we are using, that is either vertical polarization or a horizontal polarization. Why we can say that we have the vertical polarization or a horizontal polarization, because signal, we can say that whatever the we call electric field component nature, according to that we can observe that polarization. But in the satellite communication, we need to use a technique, or to increase the satellite capacity, we need to use a technique of what? A frequency reuse. Okay, we can use frequency reuse there. So because of that frequency reuse, we can employ a vertical polarization or a horizontal polarization in the same frequency band. That's why that capacity of satellite will be increased there. In the same band, we can say that in the same band, we can transmit the vertical signal as well as the horizontal signal. Means, means in the same band, we can use a vertical polarization as well as the horizontal polarization. Or we can use the left hand, or we can say that a right hand, a circular polarization. Means we can use a two technique, either horizontal, means both horizontal and a vertical polarization in the same frequency band, or a left hand and a right hand circular polarization. That's both the technique to increase the channel capacity or to enhance the channel capacity of a satellite. But if you consider that this particular polarization, we say vertical and horizontal polarization, we can use the same particular band. But a depolarization means what? Depolarization takes place due to the differential attenuation and a phase shift, and that will be caused by the non-spherical raindrops. Depolarization means what? A attenuation and a phase shift there, attenuation and a phase shift, and that will be at depolarization means attenuation of a signal or a phase shift, variation in the phase shift there, that will be occurs because of the non-spherical raindrops. Because of that non-spherical raindrop, that is nothing but a attenuation and a phase shift. Because we can say that that is nothing but a depolarization. And generally, we can say that a depolarization, or we can term the depolarization using the factor of a cross polarization, discrimination. Okay, cross polarization discrimination, that is about XPD we say, or we can say that a cross polarization isolation. That will be the I here. So means what happened here? So when we consider that a signal to be transmitted, and we have the a depolarizing medium, see here now, even here, E2 here. This is about, you can say it is nothing but a transmitter. And this one is a depolarizing medium. When your signal is transmitted here through this particular depolarizing medium, so what will occur here? What will happen? So you will get the component of E11, you will get the component of E22. Along with that, you will get the component of E21 as well as the component of E1. Okay, so means we are getting the both the component you will get that from the E1. Okay, so you can say that your signal is transmitting. Likewise, I'm just going to draw here now. We have the component of a E1 here. So we'll get that from the E1, you will get that E11 as well as you will get that E12. Okay, so means E1 we have the E11 plus a E12. And so similarly we if we consider that if we replicate that ET2 here for the E22, similarly we'll get that E21 and a E22 component. But that E21 component that will be a small here or E12 component both are the small. Means your field component that E11 and E22 is large as compared to the intensity if you consider. So here you can consider that E1 is nothing but a vertical polarized electric vector, and if you consider that E2 is a horizontal polarized electric field vector. And because of that polarization, this is nothing but a polarization medium. This one is nothing but a polarization medium. Due to the depolarization, the vectors, whatever we can say that E1 and E2 means is propagating through this, they will be rotated and they are decomposed. Rotation of this particular component E1 and E2 takes place, and they are decomposed into a vertical and a horizontal component. Which E1 will be what? E11 and E12. E2 will be what? E22 and E21. Which E11 will E1 will be E11 and E12. E2 will be what? E22 plus E21. Okay. Means your signal is propagating. We say we have the E1, your vertical transmission takes place. Now we can say that we have the a transmission of this particular even is the even signal. The received signal will be what? That received signal will be depolarized because we are transmitting the E1 because of the depolarization of this particular received signal. So we will get that a vertical component that E1 is decomposed into a copolarization component, copolarized field vector that will be of E11 in the vertical direction, and a cross polarized vector. Okay, E12 we can say we have the cross polarized vector that will be E12 in the horizontal direction. Now here E1 component when it is propagating through this depolarizing medium, we'll get that E11 will be the vertical component and E12 will be the cross polarized component, cross polarized vector component in the horizontal direction. Similarly, that horizontal vector we can say that's about E2 here. So horizontal field vector E2 that will be decomposed as a copolarized vector E22, that will be decomposed as a copolarized vector E22 along with the horizontal direction, and as a cross polarized vector that will be E21, that will be the vertical one along with the vertical direction. Now because of that, so vertical direction if you consider that means we can say that E1 is transmitting and desired is a vertical. So in that case, in a desired directions, we have the E11 that's about the desired signal, but E21 that is the undesired component. Similarly, along with the horizontal direction, when we can say E2 is transmitting, so to E22 is a desired component and E12 is a undesired component. So based on this desired and undesired component, so we can find out the cross polarization factor or a cross polarization component term. Now, so undesired component we say undesired component, that undesired component that will result in a crosstalk in an analog communication system, and that increase the BER in a digital system, bit error rate. Okay, in the digital system. Or we can say that a crosstalk analog and a BR. We can say that it increase the BR in a digital system. So we can calculate that a cross polarization desired component, cross polarization, we'll calculate cross polarization of a desired component and a that we can say that is about a isolation factor for this particular desired component. We can say that a cross polarization component, or you can say that cross polarization of a desired component, that is nothing but the wave is polarized in the desired direction to the component in the orthogonal direction. We can calculate that xpd is equal to what? A 20 log of E11 by E22. Sorry, E12. That is about a desired component and it is an undesired component. So that is about a xpd1. Similarly, we can calculate that horizontal polarization component xpd2 here.